All right. 1 week from yesterday, Monday, November 8th. Dun, dun, dun. Exam 2. So what you need to know is that it's from 7:15 to 8:45 p.m. Same rooms as last time. If you can't make that exam, hopefully you figured that out by now. And if you haven't, please check. And if you have trouble making that exam, the request for an alternate exam time, there's a little form on Canvas. Please fill that out. I've only heard from 2 of you so far. So that would be awesome if I only need to find a spot for 2 people. But I fear that's not the case. So please look at that. Check it out. It's just a Canvas survey. Closes tomorrow. So that's your last chance. Okay. What I hope to do today is get through oblique impact. Last time we got together, we talked about 2 things, colliding collinearly. And that was our regular kind of 1D impact. And now we're going to come from multiple directions. So that'll be the first half of today. And the second half of today, we'll introduce angular momentum. And then we'll talk a little bit about angular momentum next time we get together. And then I'll hopefully have a little bit of time to talk exam, if I plot everything out just right, okay? So finishing up impact today, angular momentum today, a little bit of angular momentum next time, and then a little bit of exam. That's what we got going before exam 2. Any questions on generally what I'm trying to get done? Or what we're doing on exam 2? Okay. Well, let's get rolling. So oblique impact. Kind of the same as what we did last time, except now, to make it a little trickier, we throw in one more dimension. Things aren't coming straight on. They can be coming from all sorts of different angles. So we got to reprogram the way we think about these impacts just a little bit. So 2 directions to worry about now. When these 2 things collide, the first thing we're going to think about is identifying something called the line of impact and the plane of impact. So I've just drawn these 2 things smashing into one another. And the line of impact, to find it, first we identify the point of contact between these 2 guys. So where are they going to touch? And then we draw a line tangent to both surfaces at that point. So tangent to both surfaces will look like that. This is actually my plane of impact, POI. Perpendicular to this, going through that point, that's my line of impact. So if you're super clever, you'll notice one thing that I didn't do on here is I didn't indicate at all what the direction these balls were moving. Right? If I didn't tell you that this one was coming in at this angle and this one was coming in like this, because just figuring out the line of impact and plane of impact directions, I don't need to know that. I just need to know the point they connect, and then to be able to draw a line tangent to both surfaces. So if I could do that, I could have drawn these lines any old way I wanted. These are the directions we care about. So when we see problems that are coming at multiple directions, our first step is to figure out, well, what are these guys? And then we're going to take our coordinate system and align it to whatever that line of impact and plane of impact directions are. Okay? And the reason we do that, different physics for the different sides. The line of impact direction, this is exactly like what we did last time. So for our line of impact direction, we've got these guys happening along this line of impact. We have a conservation of momentum. for the system of particles. So in this direction, we've got some internal force happening between these two balls, or cars, or whatever they may be. But that internal force, the impulse force integrated over time, is going to be equal and opposite, so it's going to cancel, right? Nothing is happening external to the system during this very short time window when these guys are smashing into one another. So we have a conservation of momentum. We've also got coefficient of restitution. So those were kind of our two equations we used last time when we were trying to figure out, well, if I look at what 1 is, I'll call 1A and 1B for now. I've got the mass of A, the velocity of A before the impact, plus the mass of B, velocity of B before impact. That was equal to the momentums afterwards. So mass of A, velocity of A after, that's the momentum of A after the impact, plus the mass of B, velocity of B after. My second equation, coefficient of restitution, we called that little e. And I've got my velocity of B after impact minus my velocity of A after impact divided by, these guys switched around. The velocity of A before minus the velocity of B before. So my line of impact direction, just like we had before, as if this was a collinear impact. Remember that impulse is going to be equal and opposite, so it's all internal. They're going to cancel. We're going to have conservation of momentum. Plane of impact direction, this is the new part. And the new part, super easy. We're going to say that in that plane of impact direction, kind of perpendicular to the line of impact, momentum is conserved for the particle. So momentum conserved just for the particle. So if I write particle A first, in this direction, so this plane of impact direction here would be like the y direction, right? So if we're here for the y direction, this is like for the x direction, and this is the x direction. So for the y direction here, if I have particle conservation of momentum, I can write conservation of momentum for each particle. So what does that look like? The mass of A times the velocity of A before the impact, plus I can put an impulse in here, plus some impulse. I'll just call it an impulse. It's equal to mass of A, velocity of A after the impact. I can do the same thing for B. But what we're going to say is that if the particle is conserving momentum, in this plane of impact direction, we've actually got no impulse. So if there's no impulse in the plane of impact direction, that means there's no force being transferred between these balls in that plane of impact direction. So whatever my momentum is before is equal to my momentum afterwards. And you can obviously just cancel the mass if the masses don't change. And you say that the velocity before is equal to the velocity after the impact for A, and the same thing would hold for B, particle B. So all we've done here is we've got our previous technique that we've used to identify what's happening in the line of impact direction. And now we want to know what's happening perpendicular to that. Well, it's all going to be based on this idea that there's no impulse acting in that direction. So I guess the way you can think of it, like try to picture, you've got your ping pong ball, which I didn't bring with me, and I'm bouncing it off this table, right? Throwing it down, it's hitting. There's some impulse on the bottom of that table that's reacting to that ball bouncing, right? Like the ball comes down, hits it, it bounces back up. But there's no impulse in the direction the ball is going. So I'm not worried about some little tiny friction happening on this table pushing back against my ball, slowing me down in that in-plane direction. So we're just going to say that that impulse in the direction along that plane of impact is 0. So that one we're going to sweep under the rug. We're only going to worry about the impulse happening in our impact direction. Am I there already? Okay. So, before I get to that problem, my steps for solving these. Everyone wants to know how to do it. Step 1. Find your line of impact and plane of impact directions. Once you do that, align a local coordinate system with those directions. So, when you figure out what the plane of impact direction is, what the line of impact direction is, hey, let's go. If I jump back a slide here, they've got X aligned with the line of impact, Y aligned with the plane of impact. If you like, that can always be your convention too. You can just keep that. But once you align your local coordinate system with these directions, then you're ready to solve these guys. So, line of impact, you're going to use conservation of system momentum. And coefficient of restitution. And in the plane of impact, you're going to use particle conservation of momentum. Or just whatever's happening before is what's happening after. And that was the y direction in our figure. Oh, not too bad. You just have to remember that certain rules apply to certain directions. And then when you take that exam next week and you flip the directions, it's not going to be that good. So keep that straight. So what I'd like to do is just draw some examples, right? This first part is the most important part. If you can figure out what these directions are, then you should be all set. So I kind of already talked about the fact that if we have two balls coming in at whatever angles, I don't need to know the directions for these balls, right? All I need to know is the fact that my rules for finding LOI and plane of impact. 1, find the contact point. Found it. Step 2, for the plane of impact, this is tangent to both surfaces and through the contact point. So, tangent to both surfaces, circle and a circle, tangent. And then step 3, line of impact is perpendicular to the plane of impact and through that tangent, that contact point. I don't want to write all that. So if I had something that looked a little different, say I have a slope and I've got a ball coming in from a crazy direction. And it's going to impact that slope. Well, how do we do this one? Step 1, find the contact point. Well, here the part of the ball is going to touch the slope. Found it. Step 2, the plane of impact is tangent to both surfaces and through the contact point. So tangent to a straight line, that one's pretty easy, straight line. Hey, this is also tangent to the circle. And it's to our point. This is my plane of impact. My line of impact, perpendicular to this, and through that contact point. So, looks like that. Line of impact. Now, put a local coordinate system on these guys. Line of impact, maybe that's my x prime. Plane of impact, whether I go down or up, it doesn't matter. That's my y prime direction. So now I have ways I can break up these velocities, and I know that parts are going to act in different directions. Some is going to act in x, some is going to act in y. But, similar to this first one, where my incoming velocity didn't matter, all I need to do was look at the geometry. Same thing's true here. Now my ball is dropping straight down from the sky. Well, that doesn't change what that contact point looks like, or the perpendicular to those planes. So, hey, same exact setup. I could come in at whatever angle I want. We could keep playing this game all day. We need to really just look at our geometry and not look at the way they're coming in. All right, now let's put one to use. So we got a cue ball A. It's given an initial velocity of 5 meters per second. There we go. It makes a direct collision with ball B, and its coefficient of restitution is 0.8. So E from A to B is 0.8. V of A before impact is 5 meters per second. All right, we were trying to figure out the velocity of B and the angle of theta after B rebounds from the cushion. So B is going to hit this cushion and then bounce off. We're trying to figure out theta and our velocity. And we got a different coefficient of restitution. E for the cushion is a little softer, 0.6, a little more energy absorbing. Each ball has a mass of 0.4 kilograms, and we're going to neglect the size. We're just going to model these guys as particles. That's what it means. So, what do we want to do? We want to find the velocity of B after the impact with the cushion, and our angle, theta. So this one's really a two-part problem. A is going to crash into B, and then B is going to crash into the cushion. So I've got two impacts to worry about. You kind of eyeball A into B. That's that one we talked about last time we got together. Collinear impact, A is going to hit B, B is going to continue moving on that same line. So that's one-dimensional. Once B hits the cushion at an angle, that's what we're talking about today. So, part one, A to B. This was last lecture. So, this is a collinear direct impact. I guess we could go kind of full on here. B is like that. A is like this. Everything's happening in this direction. First step, plane of impact, line of impact, contact point, tangent to both surfaces. That's my plane. Line of impact would be here. all of our velocity is in our line of impact direction. So maybe this would be our x prime and this would be our y prime. Y prime would be pretty boring because it's not moving at all in that direction. Everything's happening in our plane of impact direction, which is x prime. So we've really just got one set to solve. So for our x prime direction, it's a positive kind of going this way. We've got our two equations to use. Conservation of system momentum. Conserve sys momentum. And coefficient of restitution. How fast is B going to be leaving this situation? So if we use momentum first, I've got the mass times the velocity of A before impact plus mass times the velocity of B before impact. All the forces are internal, so I've got no external impulse, equals the mass times the velocity of A after plus mass times the velocity of B after. So, first thing, B is at rest. In this situation, the cue ball is being hit into ball B. Rest. We can get rid of these m's. They're all the same. All I know is I have velocity of A, 5 meters per second. That's equal to the velocity of A after plus the velocity of B after. We see that. We say, I don't have enough information to solve for these. That's where we jump into coefficient of restitution. We say our coefficient of restitution E, which is given as 0.8 for these balls, is equal to the velocity of B after impact minus the velocity of A after impact over the velocity of A before minus the velocity of B before. Just using our definitions. We've already been over the fact that B is at rest in the first before impact, so that's 0. A here is 5 meters per second. So 5 times 0.8, that looks like 4. 4 is equal to VB plus minus VA plus. Two equations, two unknowns. Velocity of B after 4.5. Velocity of A after half, 0.5. So what does this, just look at these numbers tell us that, hey, this first ball came in going at 5 meters per second. It hit, and now it's leaving faster. The ball B is moving with most of that velocity, and ball A has a little bit of it. Right? So, all right, that was old news. New stuff. I've got my cushion. I've got, this is a B, a letter B here. We just figured out what this was. Velocity of B after impact is coming in like this. We're going to assume it rolls all the way to that bumper or that cushion without slowing down. So that gets us to here. And then it exits. Velocity of B, what if I do that? Plus plus, second collision. Goofy notation, but bear with me. And we know this angle that the first one comes in at. I believe it was 30 degrees. All right, this is our oblique impact. We've got multiple dimensions to worry about, so we go through our little steps. Step 1, figure out your line of impact and plane of impact directions. How do we do that? Contact point, locate it. Where are they touching? Draw a line tangent to both surfaces. Hey, that's my cushion line. That is our plane of impact. There's no impulsive forces in our plane of impact direction. That means I've got no force pushing up or pushing down. All that impulsive force is happening in my line of impact direction, which is perpendicular. Maybe this is my x and this is my y. That's the way we like to do it. So now, maybe we'll do the plane of impact direction first. I like that one because it's easy. Whatever speed this ball is moving in the y direction before the impact is the same speed it leaves the impact with. So this guy, I can think of this as my VBY, right? The portion of VB in the y direction. Hey, this here is the exact same as it would be if I drew it here, before and after the impact. So the velocity of B in the y direction after my first impact is equal to that of my second impact. So we can go and pluck out what that is. I know that the velocity of B in the y direction after our impact, I wrote that down, 4.5 meters per second. But now I need to break this up into these components. I need to know what it is in x and what it is in y, because I really just want the y piece, right? So my y component of that is my sine 30 leg. And it's in the negative direction. So my magnitude times minus sine 30 degrees. That's what's happening in the y direction. This apparently is 2 1/4. Yep, 30 is half, so 4 1/2 divided by 2. So minus 2.25 meters per second J. So that's a plus or plus plus, whatever, doesn't matter. Unchanged, right? So I know what that part of one of the terms is coming off that bumper. Line of impact direction. This is maybe a little different than what we did before, right? So line of impact, we had two things that we looked at. The first was system conservation of momentum. You take a peek at our system here, doesn't really make quite as much sense as it did with two balls. So if I look at this, I've got the mass of the ball, velocity of the ball after impact 1, plus the mass of the cushion, velocity of the cushion after the impact, and then I use 2 pluses for after the cushion impact. All right. So if you just wrote it like this, assuming it wasn't a cushion, it was just another ball, it wouldn't really tell the story, right? We got our cushion is sitting there, stationary. Hopefully our pool table is relatively sturdy, so it's not moving. So this would just leave us with our velocity before is equal to our velocity after. But that's really not the whole story, because this guy, this cushion, would provide some impulse, right? I don't know what that impulse is. It's not going to be terribly useful for solving this problem, so we're not going to use it. Our other equation, coefficient of restitution. E, in this case we were told it was 0.6 for the cushion, is equal to the velocity of the ball after a second impact minus the velocity of the cushion after the second impact over the velocity of the cushion after the first impact minus the velocity of the ball after the first impact. This one, my cushion, still sitting still. These guys are zeros. The velocity of my ball, this would be in our x direction, right? So maybe I should put a little subscript x here to remind us that these are in the x direction. So the velocity of the ball in the x direction after the first impact, that takes us back. This is 4.5 meters per second. And in the x direction, it's minus the cosine leg, minus cos theta in the I. So this is theta is 30. This can give us, if we plugged it back in and solved, take a peek at what we have first, though. My coefficient of restitution is 0.6. I've got v of b in the x direction after the second impact over minus some negative number, which that number came from here. Right? So minus a minus, that'll be positive. Hey, that gives me a velocity of x after the second impact in the positive direction. That matches my intuition, right? Now, it was coming in the minus x direction, hits the wall, turns, and now it's leaving in the positive x direction. Hey, that's what I expect to see. My velocity of b in the x direction after that impact, 2.34 meters per second in the I. So, my velocity of b, putting these two things together, the x direction, 2.34, the y direction, minus 2.25, and these are meters per second. What does that look like? 2.34 minus 2.25. That's what we got. If I needed to figure out this angle, I could say the tangent of theta. Opposite over adjacent. 2.25 over 2.34. .1 degrees. Maybe I screwed that up. I must have messed this up a little. This angle is less than 45, right? This one's smaller than this one. 44 degrees. I don't know. You calculate it, right? If they were both the same, it'd be 45. Okay. Looping around to finish one thing, though. If I did ask you, so for my line of impact direction, I know it's a lot of junk on this screen. I told you that system conservation of momentum wasn't super useful, right? Because I had my velocity of my ball before impact, my velocity of the ball after impact, and I had some impulse from the cushion. Now that I figured out how fast my ball is exiting, I could figure out my impulse, right? I could loop back to this equation and solve for my impulse. My impulse would just be the mass of my velocity times the velocity of the ball after the second impact minus the first impact. And this, again, is the x direction because that is what we're looking at for our line of impact direction. So even though this equation won't be super useful to us, remember that, I can still get some information out of it. If I didn't need to figure out what that impulse was, provided by the cushion or provided by a table this ball is bouncing off of, we have a way to solve for that. Whole new topic now, shifting gears. So you loved momentum. Now, therefore, you'll love angular momentum. So we'll start with Newton's second law, just like we did. F equals ma. Got us to momentum. But now we'll not look at momentum going in a straight line, but angular momentum, as it's the moment of momentum, as things are maybe rotating around a given axis or a given point. So we started with linear momentum. We called that P. We said it was a vector of mass times velocity. And we had an impulse, which we said was the integral of force with respect to time. Our angular momentum, we want to define that as the moment of linear momentum. So, the moment of linear momentum. So take you back a little bit to statics. You know, what was the moment? We did R cross a force. A moment was R cross F. Our angular momentum is going to be R cross our linear momentum. So someone came in there, they really wanted their name on something. They're like, I'm just going to R cross something that's already been defined. Come up with a new theorem. Angular momentum. We're going to give that little h. Little h for momentum, angular momentum, needs a subscript, though. Just like moment needs a subscript. You need to tell me the point at which you're taking moments about. Right? So for a moment before, you found some position, and you defined some r variable. So you could do r cross f. Same thing with angular momentum. We've got to pick a point at which we're taking that angular momentum about, so we're taking it about O. And that equals r cross linear momentum. R's are just our position vector from our origin, where we're taking our angular momentum about, to the point we care about. The point we care about, hey, where's that velocity going? That's what we're tracking. So, all right. Back to Newton's second law. F equals ma. Right? This is where we started. We said A, this is like the time derivative of velocity. That was the first trick that we pulled to get to momentum. If we want to find the moment of this, just like r cross f, we r cross the whole thing. This left-hand side becomes r cross f. The right-hand side, r cross m v dot. R cross f, this is our buddy from statics. That's moment. This, r cross m v dot, we're going to show that this is the time derivative of our angular momentum. And it's not going to be painful, or that painful. We just need to go back to our angular momentum and figure out what it looks like. So, the time derivative of my angular momentum, d by dt, h0. When I take the time derivative, I got to take the derivative of the first piece times the second, plus the derivative of the second piece times the first. It's a product rule. So when I do that, derivative of the first piece, r vector dot cross m v, plus derivative of the second piece times the first, r cross m v dot. Okay. This guy is the time derivative of our angular momentum. Now look at this first piece, r dot. What is r dot? The time rate of change of my position vector. Hey, that's velocity. So is v cross itself. Any vector crossed with a parallel vector, which would be itself, is equal to 0. So that piece just falls out. These guys are parallel. So this is because r dot is parallel to v. So what I'm left with is just this, r cross m v dot, which is what I wanted to show. So, how do we use that? If I've got moment is equal to the time rate of change of angular, not a dot, of angular momentum. I already did the time rate of change by dt. I could integrate, move this t over and integrate this, right? So I'd have the integral of moment dt is equal to the integral of the derivative of h0, state 1 to state 2. This side just becomes h0 of state 2 minus h0 of state 1. And this looks like our old friend when we manipulate this. Angular momentum at state 1 plus the integral of moment dt from 1 to 2 is equal to my angular momentum at state 2 for a single particle. That's how we can actually use this. And that is an awful lot like our linear momentum. So for linear, we just had p at state 1 plus the integral of force dt is equal to p at state 2. All we did was r cross this equation, and we got to this one, right? So, whole lot of work, pretty obvious. Like, you went through all that? Moment is r cross f. Yeah, we could have just done that. Could have saved you 10 minutes of your life. You'll never get that back. Sorry. Okay. Putting it to use in 6 minutes. I'll do this one next time we get started. But maybe just, how do we calculate r cross f? It's been a while since statics and we had to do a cross product. So figure out the angular momentum of this particle about point O. So I've got a particle traveling here at A, and it's traveling on this line with a velocity of 6 meters per second. I want to figure out the angular momentum about point O. So I need to figure out, first, my vector from O to the point I care about. So my angular momentum, h0, is r from the origin to our point, crossed with mass times our velocity. Let's take the pieces. My r vector. From the origin to where I'm trying to go, that's minus 2 in the x. I just went back here. And then the y direction goes this way, minus 3. And in the z direction, I go this way, plus 4. So minus 2i plus 3j, minus 3j, plus 4k. And this is probably like meters or something. A unit of distance. Yeah, meters. My velocity. I'm going 6 meters per second. And the direction, though, the direction is the unit vector between points A and B. A to B. So for that, we've got to figure out what that unit vector is. Well, what am I doing to get from A to B? In the x direction, looks like I'm moving positive 2. In the y direction, I'm moving a minus 4. And in the z direction, I'm moving a minus 4. And then if I want unit vector, this has got to be normalized. So over the square root of 2 squared plus 4 squared plus 4 squared. So 2 squared plus 4 squared plus 4 squared square rooted is 6. Oh, luckily here, same thing. So I've got 6 meters per second multiplied by something over 6 meters per second. And that something is 2i minus 4j minus 4k. So my 6's. This is meters. Sorry. We'll cancel. All I have to do is cross product. R cross mv. My mass is 1.5. I'm going to pull that out front. My cross product for R. I, j, k. Minus 2, minus 3, plus 4. Cross with v, which I've got as 2, minus 4, minus 4. I always learn to do them this way. I rewrite the first 2 columns. Minus 2, minus 3, 2, minus 4. I multiply down and add them up, and then I multiply up and subtract those. Does that sound familiar? All right. You guys are bored. Through the magic of math. I've got 28 in the I direction, 0 in the J direction, 14 in the K direction. Angular momentum, R cross mv. R, meters, m, kilograms, v, meters per second. So, kilogram meters per second squared is a Newton times a meter. Usually we look at it as Newton meters seconds because it's moment integrated with respect to time, right? So I've got no angular momentum about the y direction, and if you look at the figure, it makes a little bit of sense because as this guy comes through, it crashes right through the y-axis, which should match your intuition, like r cross f. There's no distance between them. All right, next time we will finish up angular momentum, talk exam,